Hey, hello. Sorry to keep you guys waiting. Am I audible to everyone? Confirmation in the chat would be. Alright, alright. Am I audible to everyone? Some kind of confirmation in the chat would be useful. Sorry, it's my first time doing this. Um, okay, nice. Chalo. Okay. So, hello everyone. Thanks for tuning in. As you know, my name is Agastya, and welcome to Maths for Fun Live. This new thing which I'm starting to do because I feel like the connection with the audience is much better when you're doing it live. So, yeah. And as you all must know, today's topic is going to be proving the differentiation rules. Oh, sorry, my brush is not amazing. Yeah, so as I was saying, today's topic is going to be proving the differentiation rules. Now, these are rules we use in our daily lives as mathematicians quite often, right? Every math student knows the differentiation rules. I even love them a lot because they're really a lot easier than to do than doing it by definition, which is the correct way to do derivatives. But these are basically shortcuts which allow us to do derivatives a lot faster, and that's why math students tend to love them. But today we're going to actually be looking at the underlying proof behind these rules, right? And we're going to be trying to figure out where they come from and how we can prove them, right? Because that's the idea. Things in maths don't exist without a proper proof. I don't know why my painting program is acting up, but yeah. Okay, great. So with that being said, let's get into it, right? So there are a variety of different rules, and we're going to start off with the very, very easy ones, right? And then we're going to slowly go to some of the more interesting ones, like the power rule and product rule. But before we get into any of that, actually the first thing we should do is write down the definition of a derivative, because it's going to be very, very useful for all our endeavors moving forward. So the definition of a derivative basically says that if I've got, let's say, some function f of x, right? You'll have to bear with the slow writing speed, right? I'm going to take the derivative of this function, right? That's basically just another function describing its rate of change. So if I take the derivative of f of x, the definition of a derivative tells me this is going to be equal to the limit as h approaches 0 of f of x plus h, minus f of x divided by h, right? This is the definition of a derivative, right? And if you think about it, this kind of makes sense. All this is saying is that you're taking a tiny change in the value of the function divided by tiny change in x, right? So if you want to calculate rate of change, we do delta y by delta x, right? And a derivative is the same thing. It's just that we take very, very infinitesimally small changes. We look at it as the change tends towards 0. That's all this definition is saying. And when you want to calculate a derivative, all you do is, like, let's say if I want to calculate x squared, I would do x plus h whole squared minus x squared divided by h, evaluate that limit, and that would give me my derivative. If I want to do sine of x, I do sine of x plus h minus sine of x divided by h, take that limit, and I get my answer, which is cos of x, right? And so on and so forth. So you can use this limit to help us evaluate derivatives. But the problem is it's often very tedious to use the limit, right? It takes a lot of math and simplification. And what we've actually come the differentiation rules. These are rules which make our life easier and are in fact proved with this very definition. So with that being said, let's get into that. Let's try to prove those rules, right? Let's start off with the most simple and rudimentary rule, and that is the constant rule, right? Like, this is one of the most simple, like the simplest rules, and it's what the first thing you might learn in a calculus class when you're starting to learn the differentiation rules. Constant rule. So the constant rule basically says that if you've got a derivative of a constant, that means it's a function, but no matter the input is always equal to a constant, right? Let's call that c. This is simply equal to 0. That's what this derivative is saying. So if I've got f of x is equal to 5, that means no matter the input x, my output will always be 5, or any constant for that matter. The derivative of this function will be 0. And this makes perfect sense. The function doesn't change. I doubt we even need to prove this, but let's do it for the sake of thoroughness, right? So if this is just a constant, right, my derivative, according to the definition I've got up there, will be, let's call it of c, will be f of x plus h, right? Now, as I said, since this is just a constant, that is going to be equal to said constant, right? If the function is always, no matter the input is always equal to a constant, then it's just going to be equal to the constant, right? Minus f of x, which is also going to be a constant, and we divide that by h, right? And we forgot to write the limit. You have to take the limit as h approaches 0. Now, this is simply going to be equal to 0 over h, right? Now, 0 over h, 0 over anything is just equal to 0. And limit as h approaches 0 of 0 is the same thing, right? So, hence it's just equal to 0. Very underwhelming proof. Now, some of you might be screaming at your monitors right now, but h is equal to 0 and anything divided by 0 is actually undefined. But you see, that's not true because h is not equal to 0. We are simply taking the limit as h approaches to 0. And one of the caveats of that is that this whole undefined factor does not come in. That's how this derivative exists in the first place. So yeah, it's a very simple rudimentary proof, but it's warm up, Okay. Let's move on to the second one. My paint program also seems to be cooperating with me a bit, slightly better. This one is also very simple, but it is the constant function rule. This is one of probably the more useful ones, which we might use, whether we realize it or not, much more often in our daily life. So the constant function rule, very simple one, and also proof is slightly more complicated than the previous one, but still fairly simple, right? For the constant function rule states that if I've got the derivative of some constant into a function, let's call that function f of x, right? This is simply going to be equal to that constant into the derivative of that function, df by dx. You can write a derivative either as derivative of a function, or you can just write the function on top. So df dx is another way of writing the derivative of f of x, right? So basically what this is saying is that if you've got a constant multiplied by a function, you take its derivative, that is going to be the constant into the derivative of the function. So maybe if I've got 3 into sine of x is my function, right? If I take the derivative of that, what this rule is saying is going to be 3 into the derivative of sine of x. And we use this without knowing it a lot in our daily life when you're evaluating derivatives, or at least I do. And its proof is also quite rudimentary, right? So once again, if I want to take the derivative of a constant into a function, right, we're going to do this by definition. So that's going to be equal to the limit as h approaches 0 of the constant into f of x plus h, right, minus the constant into f of x over h, right? And I'm sure the rest I'm fairly obvious what we need to do now. All we have to do is we have to take the constant common, right? I'm not going to write the limit again, just assume it's there, right? We take the constant common and we do f of x plus h minus f of x, and we divide by h. And now what we can do is we can take the constant out, right? So this is just the limit product rule, right? So if you've got a limit of a into b, it's equal to the limit of a into the limit of b. So we can take so this can be written as limit as h approaches 0 of c. And because in this expression, right, there's no h, so this is just, we can just sort of take c out. So c is equal to into the, we can write this as c into the limit as h approaches 0 of f of x plus h minus f of x all over h, right? And once again, if you recognize, this is just going to be the derivative of f of x. If you go up here, that was the definition we defined, right? That says the derivative of f of x. We can hence write this as equal to c into the derivative of f of x, or df by dx. And that's about it, right? Sorry, my x looks terrible. Once again, a very simple rudimentary proof, but one that's useful in day-to-day life. And that's how the constant function rule is being proved, right? Great. Okay, let's move on to our next rule now. Okay. So now we're gonna, it's another simple one, but it's a little bit more complicated, little bit more to do, and that's gonna be the sum rule, right? Now the sum rule is another really simple one, right? And once again, something that we use very often without knowing when we're taking derivatives, right? And the sum rule basically states is, let's say I've got some function s of x, right? And I can write that function as f of x plus g of x, right? So it's a sum of two different functions. You could think of this as maybe 5x squared plus 2x, or sine of x plus cos of x. This can be any functions, right? But I've got one big function which is in fact a sum of two different functions. If I want to take the derivative of s of x, right, or the derivative of the sum of these two functions, sum rule tells me that is simply going to be equal to the derivative of f of x plus the derivative of g of x. So simply put, I could sort of paraphrase this as the derivative of a sum is the sum of its derivatives, right? It's a tongue twister, but basically it's just saying that if I've got f of x plus g of x, if I take the derivative of that, that'll just be equal to the derivative of f of x plus the derivative of g of x. And once again, the proof is not that complicated, but we can go through it anyways, right? So ds dx, once again I'm just writing it in the other form for the sake of compactness, is going to be, is going to be, as we know, limit as h approaches 0 of, now h of x plus h is just going to be f of x plus h plus g of x plus h. So I can write that down accordingly, right? So we get f of x plus h plus g of x plus h, and now for s of x, just write minus here, and we have to open a bracket because we're going to we're going to expand it. It's just going to be f of x plus g of x by definition. So we write f of x plus g of x, and close bracket, divide by h. Right? This is just let me draw a fraction bar better. And as you can see, this is just the definition of a derivative, right? If you want, I can put brackets here as well for the sake of completeness. So we've got the function evaluated at x plus h, and we're subtracting off the function evaluated at x. Now I'm going to distribute the minuses and rearrange the term a little bit, right? Rearrange the terms. So I'm going to take the limit as, limit as h approaches 0, and I'm going to distribute the minus, and I'm going to rearrange the terms. So what I'm going to do is, I'm going to write f of x plus h, and I'm going to then, so this will become minus f of x minus g of x, right? So I'm going to bring minus f of x here, minus f of x, and I'm going to write plus g of x plus h, and then minus g of x, because remember the minus needs to be distributed throughout this entire bracket, and I'm going to divide by h. Okay, now we can just split the fraction, right? We can split the fraction, so we'll just cut it here and say f of x plus h minus f of x over h plus g of x plus h minus g of x over h, and we'll split the limit as well. Once again, this is just the limit sum rule. If you've got limit of a plus b, that's just going to be equal to the limit of a plus limit of b. So point is, you can rewrite this as the limit as h approaches 0 of f of x plus h minus f of x divided by h plus, once again we split the limit, right, using the limit sum rule. We get limit as h approaches 0 of g of x plus h minus g of x over h. And once again, I'm sure you've noticed, this is just going, I should probably make that clearer. This is just the derivative of f of x, this is just the derivative of g of x. Once again, according to the definition we wrote in the beginning of the video, right? So I simply rewrite this as the derivative of f of x df dx plus the derivative of g of x dg dx. And that's all the, oh my god, and that's all that there is to it. My paint program is very laggy. I don't know why. Maybe it's because I'm streaming, so I apologize for all, the handwriting errors. But yeah, okay, so this is the sum rule proved, right? All we did was we distributed the terms, made the limits accordingly, and we can easily prove that this is the case, right? And I'm sure that if you have been evaluating main derivatives according to definition, you would have noticed that this is the case. But anyways, just for the sake of completeness, that's where the sum rule comes from. Now I'm not going to bother proving the subtraction rule, right? Or like the difference rule, as it's sometimes called, which is the same thing. It's just saying that the derivative of f of x minus g of x is the derivative of f of x minus the derivative of g of x. I'm not going to bother proving that because it's the proof is the exact same as what I've shown you, just with some slight differences, right? And because you can use, we've proved the constant function rule, we've proved the sum rule, you can literally use those two rules to prove the rest, right? To prove the subtraction rule. So that's why I am not going to go into proving the subtraction rule. 1 second, I'm trying to fill this so I can move on. But with that being said, so these were very simple ones. I'm sure many members of the also be aware of these proofs, right? But with that being said, we're now going to be moving on to some more interesting ones, and we're going to start off with the power rule. I'm not sure why it's not filling, but we'll have to see. Let's see if I can find some more space on the side. Okay, I'll make do with some limited space. Okay, let's move on to proving the power rule, right? So that's going to be number 4. Oh, sorry, color. Number 4. This one is once again a very useful rule, and like it's very popular as well. Many people know the power rule. So the power rule basically states that if you've got the derivative of a function which is of the form x to the power n, right? We're raising x to some power. That could be x to the power 3, x to the power 4, x to the power half, minus 1, all works, right? Oh, sorry, one moment, my cursor is frozen. But basically what it says is that is going to be equal to sorry, my screen seems to have frozen. No, sorry about that. Yeah, basically that says that that's going to be equal to nx to the power n minus 1. So by that logic, that basically means that if I were to have, sorry about that, yes, it's equal to nx to the power n minus 1. So if I had, for example, x squared, I bring down the power and subtract 1, so that becomes 2x. If I x cubed, you bring down the power and subtract 1, 3x squared. X to the power minus 1, so it's going to become minus x to the power negative 2, or in other words minus 1 over x squared, right? So this rule, nx to the power n minus 1, works for everything. It works for fractional, negative and powers, right? And what we want, and it's very useful, we use it all the time, and what we want to do right now is prove it, right? And this proof is going to be a bit more interesting and also a bit more difficult than the proofs that I've shown you so far, but hopefully we can get through it unscathed. Okay, so let me just define, to make things a bit clearer, let me just define a function p of x and call that x to the power n, right? Just to make things a bit clearer. Now to prove, let's say I want to take the derivative of p of x, so dp dx, dp dx, that is just going to be, we'll use the definition now, so limit as h approaches 0 of x plus h to the power n, right? We're just going to take f of x plus h, which is p of x plus h, which is just x plus h to the power n, minus x to the power n, right? And then we're going to divide that by h, right? Now you might struggle with this expansion here. So you've got x plus h to the power n, right? Now if it was squared or cubed, we know how to expand a plus b squared or a plus b whole cubed, right? But the problem is this is general, so it can be a bit, the end is not defined, so you might struggle a little bit. And unfortunately, the only way in which we can expand this is using the binomial expansion theorem. Now I know everyone hates the binomial expansion theorem, but believe me, I wouldn't be using it unless I had to, right? So, and actually don't worry, because we don't really need to use that much of the theorem, because you'll see a lot of things cancel in the end. But basically the binomial expansion theorem, let me see if I can, there's no need to write it, but if I'll just write it in the corner here, let me just make a small box. Basically says that if you've got a plus b to the power n, right, that is going to be equal to the sum when n is between r is equal to 0 till n of n choose r. This is just a combinations formula, so you're taking n combinations out of r, and there's a formula for it, but we actually, trust me, we don't need to worry about this part too much. And we're going to have a to the power, so we're going to have a to the power n minus r and b to the power r into b to the power r, right? This is the binomial expansion theorem, and we're going to be using that here, but don't worry, it simplifies quite a bit. So basically we can say this is going to be equal to the limit as h approaches 0. I'm not writing it again, but hopefully you get the point. And now we're going to open this up, right? So this tells me that the first term is of course going to be x to the power n, right? Next term is going to be nx to the power n minus 1 into h, right? Just using the binomial expansion theorem. And then let me just write it like this, n choose and choose 0 and choose 1 and choose 2, right? This is some constant, right? This is some constant which you can evaluate, but trust me, it doesn't matter in the end. X to the power n minus 2 h squared, right? And we sort of seem to have run out of space here. But anyway, this keeps on going until it ends, and then you've simply got, let me do one thing. Let me erase the fraction bar. 1 second. Okay, yeah. So we'll keep on going until how much it needs to go, until you get h to the power n, and we're going to subtract off x to the power n, because remember that term is still there, right? And we're going to divide by h, right? Okay, now one thing you might immediately notice right off the bat is, sorry for the current writing style, but x to the power n and x to the power n cancel. So you're adding it and subtracting it, they equate to 0. And you've just got this sort of series going on here, which is just an expansion of the binomial, right? But now what you notice is each one of these terms has h, right? By definition. So you've got nx to the power n minus 1 of h, then n choose 2, x to the power n minus 2 h squared, and this will keep on going. Every term will have h until you reach h to the power n, right? With n choose n, but yeah, you'll reach h to the power n basically, right? And each one of these terms has h. So by that token, what we can do is we can take h common. I'll take advantage of some more space I've got here. So we can take h common, right? And if we're taking h common, we have to subtract 1 from each power. So in that case, we get nx to the power n minus 1. And we've taken h common, so it'll just be that. Then we've got plus and choose 2. This is just some number, it's a constant, right? Of x to the power n minus 2 h, right? Because it's h squared, but we've taken h common, right? And this will keep on going like this until it ends at h to the power n. I can just, for completeness, let me just write h to the power n minus 1, right? And you can then divide by h, right? And h and h cancel, and so we're left with the limit as h approaches 0 of, sorry, one moment, we're left with the limit as h approaches 0 of nx, oh wait, sorry, nx to the power n minus 1. Oh. Sorry, my paint program seems to be acting up. Nx to the power n minus 1 plus n choose 2 of x to the power n minus 2 h, and ongoing until you reach h to the power n minus 1, right? And now minus 1, okay, right? And now what you notice is that, so we got to take the limit as h approaches 0, and what you notice is that aside from this first term here, every term has h, right? So as h approaches, and it's multiplied by h, I should say more accurately. So every time as h approaches 0, all these terms will also approach 0, right? So no matter what x to the power minus 2 is, if you're multiplying it with 0, it will just be equal to 0, right? So once again, as h approaches 0, all these terms which have h in them, or which are multiplied by h, will also approach 0. So I can simply write this as nx to the power n minus 1. Oh. Nx to the power n minus 1, right? So another simpler way to recap, right? In the binomial expansion theorem, right, the first term is x to the power n, second term is nx to the power n minus 1 h, and then you have a bunch of other terms which have h in, which include h, right? H squared, h cubed, so on and so forth, until you reach h to the power n, right? Now we firstly the x to the power n, x to the power n cancel, and we take h common, right? And then everything except this first term has h, so then we cancel h, and once again everything except this first term has h, right? So as the limit of h approaches 0, all those terms will also approach 0, hence we just left with the first term and x to the power n minus 1 as our answer, right? And you can confirm that this works by proving a variety of different functions using definition, but yeah, this is the proof for the power rule, right? And so hopefully that was a bit more interesting and a bit more complicated than some of the other proofs we've been going through. And now we've got two more to prove, the product rule and the chain rule, right? Chain rule is actually slightly simpler to prove, but I'll be proving that one later. First we start with the product rule, but I don't want to run into the same problem again. Okay, actually no, but we have enough space, so I'll make do with it. Let's prove the product rule. Okay, this will be what, 5, right? Yeah, okay. Product rule, right? Now the product rule one of the less used rules, but a favorite of calculus examiners. So if you're giving a calculus exam, you'll often find a lot of product rule and quotient rule questions, right? They love to give you product rule, quotient rule, and chain rule all in one question. Actually, sometimes you get questions like that. But yeah, basically the product rule says that if you, let's say I've got some function L of x, right? And now L of x is equal to f of x into g of x. So this could be, once again, f and g can be anything, right? It could be sine of x into cos of x, phi of x into ln of x, right? Two functions multiplied by each other. How do I take this derivative, right? The product rule tells you that dl dx, right, the derivative of L with respect to x is equal to, let me write it in Leibniz form only. So you get df dx into g of x plus f of x into dg dx. So basically, it's not df dx into dg dx, right? It's not that. It is df dx into g of x plus f of x into dg dx. I'm writing this in what you call it, Leibniz form, just to remain consistent, but you might have seen it in a more compact form like this: f prime of x. This is just another way of writing the derivative of f of x, g of x plus g prime of x, f of x. It's the exact same thing as what I've written, but I wrote it in Leibniz form just to be a bit more consistent, because that's what I was using throughout the rest. So yeah, just in case you were wondering, if you like, I just wanted to make sure that it's clear that those two are just the same, right? So now this one is quite difficult to prove, right? But hopefully we'll get at it and we'll see that it's actually not as difficult as we might think, right? And the crux of this lies in that what we have in terms of a general formula, it's not in terms of some derivatives, right? It's not. It's kind of messed up. So what we want to do is we want to rearrange it algebraically to get it in terms of the derivative of f of x and the derivative of g of x, right? Because that's what we know. So what do we know? Commonly we know, if you've got two functions multiplied by each other, we know their derivatives. So what we want to do through this is sort of rearrange it algebraically in a form where it's in terms of the function's derivatives. That's the goal going in. The reason I'm sharing this with you is, if you were trying to prove it yourself, it may seem that I'm just sort of stating things one after the other, and you may not come by this yourself. But remember, when you want to prove differentiation rules yourself, just try to get it in a form where you have the derivative of one function or another, right? That's the best policy. But with that being said, we can just start proving it, right? So dl dx, according to the definition, right, will be equal to the limit as h approaches 0 of f of x plus h into g of x plus h, right? And we're going to subtract off f of x, g of x, because remember, L of x is just the product of two functions, f of x, g of x, right? So we're just evaluating f of x plus h and g of x plus h at different, evaluating both functions, right? And we'll divide by h. Yeah. Okay, great. Now, as I said, in this form, it's not very favorable, and we definitely have not converted it into like that, right? So what you want to do is, let's try to isolate these terms, right? Because you can see you've got f of x plus h here, f of x there. You can see how you might be able to sort of algebraically manipulate it so that you can somehow maybe get a derivative out of it. So let's try doing that. So the first step what we're going to do is we're going to split the fraction, right? Right now it's this and it's that. Let's split it. So this is just going to be equal to, we're going to need all the space we can get. One moment. Yeah. So it's going to be equal to the limit as h approaches 0 of, f of, my god, it's lagging so much, I apologize, f of x, what's going on, f of x plus h, okay, it's back to normal, g of x plus h, I'm going to divide by h. Once again, we split the fraction, so we just say minus f of x, g of x divided by h, right? So this is our new thing. We can split the limits later on, but it's not really necessary right now. In fact, we shouldn't. So with that being said, let's move on, right? Now, Well, let's look at this. Let's focus our attention on this fraction first, and let's see what we can do with this, right? So we've got f of x plus h, and we've got g of x plus h, right? Now, let's say I want to make this f of x's derivative. I want to somehow get f of x's derivative in here, right? So first things first, this g of x needs to go out, right? Because we can't, f of x's derivative is only in terms of f of x. So we need to somehow get rid of this. Secondly, we need minus f of x to come, right? We need minus f of x to come, okay? So what we're going to do in this case is we are going to, and we can have it multiplied by something in the end, but what we want to, we sort of want to isolate the derivative out, right? So we're going to, let's sort of come, we can write this in the end, but basically we want to focus on this fraction right now. So what we're going to do is we're going to we're going to construct an expression and put it in both the numerator and the denominator of a fraction and multiply it, right? So that we can get to where we want to go. So let's stop talking in the air and do the maths, right? So this is going to be equal to the limit as h approaches 0 of f of x plus h, g of x plus h, all divided by h. And now what I'm going to do is I'm going to multiply it by minus f of x, g of x plus h, right? And we're going to divide that by itself only, right? Minus f of x, g of x plus h. So this is just equal to 1, right? As you might notice, this is just equal to 1, right? So we're not changing the value of this expression, we're just multiplying it by numerator and denominator. And what we'll do is we will then subtract off f of x, g of x over h on the side. I'll just put that down. Minus f of x, g of x over h. Okay, great, right? So now what we're going to do is, oh sorry, I did it incorrectly. Yeah, no, what we're going to do is we're going to add them, and this is going to be h. Sorry, got a bit nervous. So the numerator is what we want it to be, but if you put that in, multiplication is not what we wanted to. We wanted to add them, right? So what we're going to do is we're going to just keep this h. We're going to keep this h, and we're going to subtract off the same fraction, right? Sorry for that. So we're going to subtract off the same fraction. So in fact, the easier way to write this would just be, let me just erase this here. Sorry for the confusion. So we can write this as, we're going to minus, and then we'll just add on the same fraction, right? This is the same fraction. So sorry for that confusion, but basically what we're doing is we're taking this fraction, we're both adding and subtracting it, so they'll cancel, so the value doesn't change, but we're going to group these two fractions together. Sorry about that. I got a bit nervous, but yeah, this is what we're going to do, right? And this fraction is still there. So what we're going to do now is we're going to fuse the fractions, right? So we're going to say this is equal to the limit as h approaches 0 of f of x plus h, g of x plus h, and we'll just bring the two fractions together, minus f of x, g of x over h, right? We just brought these two fractions together, and let's bring these two fractions together as well, right? And you'll see why in a moment. Let's add on. Remember, this is just the positive version of this, so we have g of x plus h. Just want to make sure that's clear, right? F of x plus h, f of x, g of x plus h, minus f of x, g of x over h, right? So we were adding and subtracting the same fraction, and we fused these two and these two, right? That's what we've done. F of x plus h, g of x plus h, minus f of x, g of x plus h, and same thing, but we fuse these two fractions together, right? And now what here I'm going to do is I'm going to take g of x, okay, because you can see it's within both terms. And here what I'm going to do is I'm going to take f of x common, because it's there in both terms. So by doing, when I do that, you'll see that this is equal to, simply equal to the limit as, sorry about that, the limit as h approaches 0 of, we're taking f of x, g of x plus h common on this side, right? G of x plus h into, we have f of x plus h minus f of x over h, because we just took g of x plus h common, and then we'll add on, we're taking g of x f of x common here, so f of x, we open the bracket, or we don't need to, g of x plus h minus g of x, sorry about the cramp space, and over h, right? And we can distribute the limit, right? And what you notice is that if we take the limit as h approaches 0 of this, well, let's look at this side, right? So g of x plus h as h approaches 0 will just be g of x, right? And this, the limit as h approaches 0 of this expression, that's just the derivative of f of x, as we proved, right? Similarly here, f of x is, that's just going to be remain f of x, and we take the limit as h approaches 0 of g of x plus h minus g of x, that is just going to be the derivative of g of x. So taking this limit, we can just rewrite this entire thing as g of x into df dx plus f of x into dg dx. And this is the exact, I just wrote it in a slightly different order, but yeah, this is the exact product rule, right? So what we did was we added and subtracted the same fraction, and we took things common to convert it into a form where it was in terms of the derivative of f of x and the derivative of g of x. Sorry for multiplying instead of adding, I just made a mistake there. Yeah, okay, great. Now we're going to move on to proving the chain rule, but I've clearly run out of space, so I'm going to try to remedy that. Give me a second. Yeah, so till then, so basically the chain is when you've got nested functions, right? So when you've got f of g of x plus f of g of x, right? So if you've got one function and you've got another function nested inside of it, right? So maybe sine of cos of x, where the input of one function is the output of another, right? These aren't as common, but they come up in places you might not expect, right? And once again, the chain rule is very, very useful. So let's say I wanted to take the derivative of, I'll just erase it. Let's say I wanted to take the derivative of ln of x squared, right? Well, you might just think that, oh, I can just take x but an x squared, but it's not multiplication. It's they're nested inside each other. They're called compound functions, right? So that makes it very difficult, right? And when you've got functions like this, where the output of one is the input of the other, right? We tend to use the chain rule. It's one of the more advanced concepts of differentiation, but still in calculus 1 only. So we can go ahead and prove, and then we can use the product rule and chain rule to prove the quotient rule, right? Because it's the quotient rules proof is just it's messy, right? And why go to the trouble? Okay, so let's prove the chain rule. That's going to be number 6, right? Yeah, chain rule. Now the chain rule basically states that, let's say you've got some function h of x, okay, and h of x is equal to f of g of x, like I was saying, right? Nested functions. So the chain rule basically refers to this function's derivative. So if I take dh dx, the chain rule tells me this is going to be, if I write this in Leibniz form, it will be df dg into dg dx. This is writing it in Leibniz form, right? I'll write it in the more commonly known form, right? If you write it as prime function, right, you can write this as f prime of g of x into g of x. This is the more common known, like this is the more commonly used form amongst math students, right? So you have the derivative of f of x, where you putting g of x as the input into the derivative of g of x, right? So let's say if I've got sine of x squared, what this is telling me is that I have to take the derivative of sine of x and put x squared as its input, and then multiply that by the derivative of x squared. So I know the derivative of sine of x is cos of x, and I know the derivative of x squared is 2x, right? So I can write this as cos of x squared into 2x. That's what the chain rule is basically telling me, and we want to prove this, right? And the proof for this is thankfully a lot easier than the one I just did with the product rule. Okay, so we're going to say this is equal to the limit as h approaches 0 of f of g of x plus h minus f of g of x all divided by h. Once again, this is just the differentiation. This is just a definition of the derivative, right? Okay. Now, once again, we're going to split the fractions, right? We're going to split the fractions. So let's do that. So limit as h approaches 0 of f of g of x plus h divided by h minus f of g of x, f of g of x over h, right? And now what might trip you up here is looking at this from the proper perspective, right? You've got one function sort of nested inside another. How am I even supposed to take this derivative? It makes no sense, right? And the answer to that is to notice Leibniz form. When you look at it in Leibniz form, it reveals something very important, right? So you've got df dg. So here, because we've got g of x as the input, it's going to be very difficult for us to algebraically manipulate this into the form where I just have df dx and dg dx, right? It's going to be very, very difficult for us to do that. So instead, what we're going to try to do is, instead of taking our derivatives exclusively in terms of with respect to x, we can take some derivatives with respect to g, right? So as you can see, what we have here is, so as you can see, what we've got here, we've got g of x plus h, right? But we've got g of x plus h here, right? So what we can do is, because this is the input of f of x, we can take it in terms of g, right? So if we can have, what is this referring to? So df dg means a tiny change in f of x divided by a tiny change in g of x, right? So if we can if we can manipulate this into a form where we have a tiny change in f of x over a tiny change in g of x, we can simply rewrite that as the derivative of x with respect to g of x, right? So instead of taking the derivative of a function with respect to x, we take it with respect to another function, right? That is the hint with which we need to work to prove it, right? Because algebraically we can't get this only in terms of f of x, df dx and dg dx, right? In fact, on second thought, we don't really need to split the fraction. It's not really necessary, so let's not, right? We can just keep this minus, okay? It's not very necessary to split the fraction. Okay, so now what we're going to do is to sort of remedy this, right? We'll take the limit as h approaches 0, and remember, we want a tiny change in g of x at the bottom, right? So what we're going to do is we're going to multiply this by g of x plus h minus g of x, right? That is literally a small change in f of x, right? Because we're taking a limit with respect to h. That's what we want, right? So we want a tiny change in g of x in the denominator, right? So that's why we're going to take g of x plus h minus g of x. We're going to multiply that in both the numerator and the denominator, right? Just for the sake of completeness, because we don't want to change the value of the expression itself. So this is going to be f of g of x plus h minus f of g of x divided by h. We're going to multiply this by g of x plus h minus g of x. This is just a tiny change in g of x, right? Divided by g of x plus h minus g of x. And we're going to multiply them together, right? And once again, this is just equal to 1. So we're not changing the value of the expression, but we're going to be able to do some algebra to sort of simplify it into another form, right? And so I'm going to rewrite this as, in fact, let me skip a step because let me just skip a step to make it a bit more clear, right? Because if I write it all in one, it might be a bit messy, right? So what we're going to do is we would have this into this divided by that into that, right? So now what, after having it written it like that, I'm going to split it, right? And I'm going to rewrite it as f of g of x plus h, same limit, right? F of g of x plus h minus f of g of x, and we're going to divide by g of x plus h minus g of x, right? And we're going to then multiply by g of x plus h minus g of x, and we're going to divide by h, right? And once again, what I've done here is that I skipped a step, right? But because it would, if I wrote it down in full, it would be a bit more messy, right? So we multiply these two together, we get a into b upon c into d, right? And then I keep this one here, and I take that one there, right? Because we can rewrite it in any way we want, right? This is just fraction multiplication, right? So I just brought this here and I took that there, right? Same thing, when we multiply these together, it yields the same fraction only, but I just split it in a way which makes it easier for me. Now what you notice about this is that I won't do a super formal proof here because that wastes a lot of space really, right? But what you notice is that we've got, as h approaches 0, right, we get a tiny change in h of x, right? A tiny change in h, because f of g of x is h of x, right? We get a tiny change in h of x, right, divided by a tiny change in g of x, right? And then we get a tiny change in g of x divided by a tiny change in x, right? This I can write as dh dx, sorry, dh dg, and I can write this as dg dx. Yeah, sorry, the upar wala I had written slightly incorrectly. It's going to be dh dg, yeah, dh dg. So this is the more common form, and so dh dg is equal to that, right? Once again, I am not going, if you wanted to make this a super formal proof, what you could do is you could split the limit. You could write g of x plus h as some variable a, g of x as some variable b, and then rewrite the entire limit as f of a minus f of b divided by g of a minus g of b, divided by a minus b, limit as a approaches b, right? And that is just going to be the derivative one. That's the second definition of a derivative. So if you wanted to make this proof super formal, that's how you would do it. But I don't think it's necessary for this particular live stream, so I won't do that, right? And I'm sure the intuitive sense I gave you is perfect, right? So we've got a tiny change in h of x divided by tiny change in g, so that will be dhg. We're going to multiply a tiny change in g of x over a tiny change in h, that is dg dx, right? And that's the chain rule proved. Okay, now we're going to, for the last proof, right? This is not going to use, what we're going to do is we're going to prove the quotient rule using the product rule and the chain rule. Now we've proved both of those, so that's perfectly valid, right? So instead of proving it by definition, which will be very tedious and very time consuming and very messy, right, we're going to use two of the rules which we have already proved to prove the quotient rule. That's the most efficient way of going about it, and it's completely mathematically sound because we've already proved those two rules, right, just in front of you. So yeah, let's just make some, we won't require too much space because we're using rules at this point, right? So yeah, now I'll just bring this down to 10, 11. Okay, now to prove the quotient rule, right? The quotient rule basically says if you have some function, let me just write down 7. If you've got some function q of x, right, which you can write as f of x divided by g of x, so some function f of x divided by another function g of x, right? Sorry. F of x divided by g of x. If you got one function divided by another, right, and you want to take its derivative, then what you need to do is, the quotient rule tells you, I won't write this down in Leibniz form because it'll explode then, it won't be legible, so I'll write it down in the prime form, right? So dq dx is equal to f prime of x into g of x. This is just the derivative of f of x, right, but it's another way of writing it, into g of x, g of x minus f of x into the derivative of g of x, g prime of x, and we divide that all by g of x squared, right, or g of x whole squared, right? This is a, you might like, it's a ginormous rule. This is the one students tend to have the most difficult time remembering, right? But it's very useful when you've got functions divided by one another. And in general, what we can do with this kind of a rule is that instead of, once again, you can imagine if we try to prove this by definition, it would be a big mess. So instead we're going to use the product rule, and we can use the product rule, power rule and chain rule all together to prove it, mainly because the way you can do that is you can have f of x and you can write that as 1 over g of x. So f of x can be written as 1 over g of x, right? So you can have it, so just one function into another, right? Actually, let me, for full completeness sake, right, I can show that f of x into g of x to the power minus 1, right? So here what we can show is that it's just a way of rewriting this, right? So here we've got a power and multiplication and sort of a nested function. So that's why we're going to use the chain rule, product rule and the power rule to prove it, right? So by converting it into this form, we're going to prove it. So how? So okay, let's do it, right? So this is first and foremost two functions multiplied by each other, right? So we're going to write this as, we're going to use the product rule here, and we're going to take the derivative of the first we'll take the derivative of the first function, right, which is f prime of x. We're going to multiply that by this just a second function, that's 1 upon g of x. Then we're going to multiply, then we're going to add just the first function f of x into the second function, so into the derivative of the second function, right? So now we're going to use the chain rule here, right? And the chain rule tells me first I need to take the derivative of the outside, right? That's going to be negative 1 upon g of x squared, right? So you need to take the derivative of the outside function with respect to the inside function, right? And using the power rule, or just using, by definition, we can see that if you got 1 upon x, the derivative of that is negative 1 upon x squared. So I can rewrite this as negative 1 over g of x squared, but we're not completed because this was a nested function, so we got to multiply this by the derivative of g of x, right? Now here what we're going to do is, let me just write this as a fraction now. We're going to write this as f prime of x divided by g of x. I'm going to add on, sorry, we can just we'll bring the minus 1 to the forefront, minus f of x g prime of x divided by g of x squared, right? Divided by g of x squared. And now what we're going to do is, so this is a perfectly usable, like we're done pretty much, right? It's perfectly usable, but to clean it up a bit more, right, to make it a bit more usable, right, instead of having two fractions, let's try to convert it into one fraction by making the denominator the same, because it can very easily be done. So let's try to do that, right? So what you'll notice is the the denominator of the first fraction, right, is g of x, and the denominator of the second fraction is g of x squared. So let me multiply the numerator and denominator both by g of x of this first fraction. That will be f prime of x into g of x, sorry about the bad handwriting, divided by g of x whole squared, because I multiplied both numerator and denominator, right? And we have to subtract off the same, right? I'll just write like this, which when we put the fractions together, we get f prime of x. Oh, let me go to the side a bit. Let me clear out some more space as well. F prime of x g of x, oh sorry, g of x g of x, sorry, my paint program is lagging a lot. Yes, sorry, bear with me please. Yes, and then minus f of x g prime of x g prime of x all over g of x whole squared. We just combine the two fractions into one, right? One second, sorry, that looks like a modulus. Let me just make the bracket properly. And square. Okay, yes, done. So this is we already proved the power rule, the product rule, and the rule. And now what we've done is we've used all three of those rules which we proved to prove the quotient rule, right? And the quotient rule is actually you don't actually need the quotient rule, right? It's not a very essential rule, because as I said, with any two pairs of functions, you can just use the power rule, the chain rule, and the product rule together to prove it, right? But the quotient rule, the situation comes up often enough where you have one function divided by another, that it's good to have a dedicated rule for it, right? Now if you really wanted to, you could prove this rule by definition in much the similar way in which you prove the product rule, right? Similar, just a lot more convoluted. But instead of doing that, it's much easier and it's much more streamlined to first prove the power rule, product rule, and chain rule, and then use those three rules to prove the quotient rule. And with that being said, we're done. These are all the mainstream derivative rules. Now there are more. There's the exponential rule. There's the logarithmic rules, right? And I won't go into those for this live stream. If you are interested, let me know. I can prove sort of the more advanced differentiation rules anytime you'd like. Sorry about this live stream. Like, it turned out a lot worse than I expected because of some, like, I don't think my laptop can handle properly streaming live, so the Paint program was just completely messed up. But yeah, well, there's a first for everything, and I think for the first time it was a pretty good experience. Let me know, give me some feedback. Do you think we should do more of this live business, or were you not really understanding and you don't want this anymore? I appreciate any feedback from all viewers. And yeah, so thank you so much for coming out to view this live. I really appreciate all who are watching, and hopefully you learned something valuable and important today. Because remember, like, you can learn formulas in school, right? And you can mug up any n number of formulas, but the best learning comes when you understand those formulas, or better yet, prove them yourself, right? Because from the proof you understand where the formula comes from, right? And you feel much more confident being able to use it. And later on, when you're working, if you want to become a mathematician, your literal career is just proving formulas, right? And then you have to prove it from scratch where you don't know the answer, right? So it's a very good practice to understand the proofs of all the formulas which you're using, right? And it's an even better practice to try to prove them yourself without looking up the proof, right? In fact, all the I did that. So before looking up any of these proofs, I try to prove them all myself, right? But why? Because that gives you the best learning. You understand the formula in ways you otherwise wouldn't have understood, and it trains your mathematics skill to the next level, where if you want to solve real life problems which no one has solved before, those muscles can be used to do that as well. So once again, never underestimate the value of a proof. That's all I'm saying. With that being said, I'd like to thank you all for coming out today, or tonight, I guess. And with that being said, I think we can end the live stream. Thank you so much for joining me today.